Let's try to understand the basic idea of string theory. So let's first start with the question that what do we mean by when we say strings? So when we normally talk in physics about a particle, we consider it to be a point particle. And then if we say that the particle has to travel from some point P to some point Q, right? We say that the trajectory of the particle might look something like this. So it has started its journey from point P and ended its journey at point Q. Now, this trajectory in physics, we call it the world line. Now, what if we say that the particle is not really a point particle, but it's rather a string, right? And a string may look something like this. And then you can say that suppose that the particle starts its journey from this, well, place and has to go to this place. So we'll take this part and we'll say that it maybe it traveled something like this, right? And you can say that this the trajectory of the particle may look something like this. Now this thing is really what we call a world sheet. So the idea really behind strings is that rather than considering of particles as point particles, we say that there are not point particles, but rather there is something that is a string, and the different patterns of this vibration of these strings may correspond to different types of particles, right? So that's really the idea of strings. The next question that might be bothering you is, why do we need strings at all? Why do we consider this option of having, instead of point particles, why do we need something that is like a string like thing? So the really thing is that we have a clue that leads us to the string theory, and that clue is really what is called the short distance problem. And this problem occurs in gravity. Well, really, to be precise, it occurs in quantum gravity, right? So it's a problem of quantum gravity, which is called a short distance problem. So let me try and demonstrate that for you. If you look at this figure that I have just drawn, two lines like this, what's happening over here is really that we have two particles, and these particles are propagating in space time freely without any interaction. What might happen is that these two particles which were moving freely, they might interact with each other by this exchange of graviton. So they might interact as an attractive force, and so that could happen by the exchange of graviton. So this diagram is really referred to as a correction to this one with one graviton exchange. You might have another possibility as well, where these two particles have now interacted with each other by an exchange of really two gravitons, and so this is called a two graviton exchange corrections, right? Now this one graviton exchange thing is really, it is proportional to Newton's constant, which is Gn, which is the universal gravitational constant as well. You might refer it to that way. And you can, if I say that I choose h bar is equal to c is equal to 1, which are the natural units, physicists often work with these units, then it has the units of this thing has the units of length squared or 1 over mass squared, right? So these are the units for this thing, which you can say that hence that Gn is equal to mp minus 2. Now, where mp is really known as the Planck's mass. And the value for this Planck mass, let me write it over here, is almost 1.2 into 10 raised to power 19 giga electron volts. Now, suppose that for this process we have E as the characteristic energy for this specific process, then the dimensionless ratio of one graviton exchange to the original process amplitude is of the order E squared over the square of Planck mass. Now, this thing, it is really an irrelevant coupling which grows weaker if the distances increase, right? So as the distances will increase or at any longer distances, this thing is going to grow weaker, right? The coupling will grow weaker. And so when you have in particle physics, we have energies of in particle physics we have energies which are, well, hundreds of GeV, right? So you can just, let's just write it as hundreds of GeV. At that point, this thing really becomes negligible. Now, because of course you can see that, look at the value for Planck mass, and energy is only hundreds of GeV, and so this whole thing would really be very small, and hence it can be ignored. Now, on the other hand, really, if the coupling will grow very strong, if we have energies which are, you can say, greater than the Planck mass, right? So in that case, the coupling will be so strong that the perturbation theory would break down. Now, this thing really shows up in the, or you can say that this thing shows up as, or it's also known as the non-renormalizability of your theory. That is, if I consider, for example, this two graviton exchange thing, then we can see that the two graviton exchange correction, let me write it over here, two graviton correction is something of the order where I have mp minus 4 integral infinity dE prime E prime cube. Now you can look at this thing, at this integral, where this E prime is really the energy of the virtual state, and this thing will diverge if I extrapolate my theory to high energies, right? So if I have very high energies over here, then this whole thing this integral will diverge. Now, there are several, or you can say mainly two possibilities for this. And one of them is really that the theory has some non-trivial ultraviolet point, right? And it's fine at your normal high energy scale. And the other thing is really a hint at new physics, which I'll explain. But that really means that there is some new physics that lies at some energy, and the extrapolation of the low energy theory after that point is not true or it's invalid. Now, string theory really has this reputation, or you can say that it is stands as something that is very hard or very challenging for someone. But and of course, if you go into the details, the mathematics of string theory, it is extremely challenging, and you're left scratching your head sometimes as well. But the basic idea is really quite natural and pretty much straightforward, which, as you follow along the video, you will also agree to. Now, the Einstein's picture is pretty simple, and it has a very neat, or you can say straightforward, geometric interpretation. So, for example, you consider that you have a particle, and this particle is going to travel around a space time. It will travel through this space time, and what it's going to do is it's going to trace some curve, right? Or you can say this path that it traces to move to this point. Now, this path, as we already discussed, is called a world line, right? Now, you can write down the action for this, and the action is just equal to some factors, and it is also equal to the length of this world line. You can write that as ds, and then you can use the principle of least action, which will tell you that the particle chooses that particular path which is the shortest for this particle, right? So it will choose the shortest path that it can while it's traveling between these two events, or you can call them points or events. Then you have this thing which is called now the string picture. You might just call it something like that. And what it does is it replaces the role of a particle with a tiny loop, you can say, of a string, something like this. And in case of a particle, as you saw, it traced out a one-dimensional curve. As it moved, as it, or you can say, traversed around or through the space time. The string really traces out something that looks like this, which is, you can see, it's a two-dimensional thing. It's really a two-dimensional surface. So that's the case of a string. And just like how we call the particle case a world line, line mainly shows that it's one dimensions. We call this a world sheet, where sheet is telling you that it's something two-dimensional, right? It's a two-dimensional surface. You can think of this situation if you were to imagine really imagine a bubble. So you can think of this string as a bubble. Now this is a bubble, and you can, it as it flows through the air, it will trace out a path, something like this, and it reaches this point, right? Now this path that the bubble traces out as it moves through the space, this thing is then called a world sheet, right? Now, the next thing for this string picture is that you need to have a principle of least action for this string. Now, what we want to do is we want a way to write down this principle of least action for the string. Now, if this natural action for a particle was simply the length, as we saw in this world line, it's the length of this world line, then the most, you can say, obvious generalization for the string case is just the area of this sheet, right? So in the two-dimensional world, length is really replaced by area. So our goal would be to express this action for the string in terms of the area of this world sheet, which would trace this loop of string traces out in space time, right? And so while we are doing that, we'll also understand the mathematics of the geometrical surfaces that follows along. So at first, let's ignore the whole thing, the string theory and Minkowski space-time and all those exotic words. We'll just for some time, let's keep those aside and let's try to understand some of the mathematics behind areas, right? So, for example, if you were to have a coordinate system. Let's draw a coordinate system where you have a y-axis, you have an x-axis, and you also have a z-axis. So it's a three-dimensional system. And let's just say at this point, you are in this xy plane, and considering the bubble, if when the bubble moves through the air, it will leave behind really a two-dimensional surface. So which will be, you can say it would be glued onto, or it would be embedded in this three-dimensional space. So this path, you can assign a function to this path, and you can say, let's call that function some capital X, and this is really a function of some parameter lambda. Now, writing down the coordinates of space using this function, we would have x, let's use small x, y, and z. So these would be the coordinates, and this is defined as this function because we don't really have a surface at this point. We are considering a line in space really at this point. So that's why we have specified this curve with this x and a function x, which is a function of this parameter lambda, and lambda is just a parameter along this curve. And this entire function x of lambda, what it really tells you is how every point lambda in this space gets mapped to a point x of lambda in the three-dimensional space, right? Now let's consider another example where what we are really doing is we are now considering, instead of a one-dimensional thing, let's consider a two-dimensional surface, right? Let's promote it to a two-dimensional curve really. And so that we know we would have something like this, right? And then we would need not just lambda, but we would also need another parameter, and we'll call that parameter, let's say, sigma. Now you can specify the surface, this entire surface, using a function which is really a function of these two different parameters. And this function really is going to tell you how every point lambda and sigma in a two-dimensional space gets mapped to a point which is you can find that point by x of lambda and sigma in this three-dimensional space. Now you can think of this sigma really as you can think of it as a direction and as a circle really, and lambda can be thought of as a line. So what I really mean is that if you consider, let me draw a cylinder like thing. right? And you can consider lambda, which moves along this way, and the direction sigma is really something that is covering this circular path. And so together, lambda and sigma is really a surface of this cylinder. Now, when this function x of lambda sigma maps the cylinder into this three-dimensional space, then it can get wrapped around to make a curvy surface, right? So all of this is well and good. Now, we have a question at this point, which was the question of areas, and that still remains. That suppose now if you have all of this thing, you have this function x of lambda and sigma, so you have this surface. The question is, how do I find the area of this surface? How do we compute that? So what we'll do is we'll think about a rectangular area of a space. Suppose that this rectangular area has some width, which is, let's call it d sigma, and it has some length, and let's call that d lambda, or you can call it as a length or a height or whatever. Now, this little region d sigma and d lambda, it will map onto another little region of the surface in the three-dimensional space, which would have some tiny area, you could say dA. Now, once we have this information, now it doesn't really have to be a rectangle, and that's because the map by this function x, it can distort the shape of this whatever you have, rectangle or whatever. So in really reality, the shape would be of more of a parallelogram. So if I draw that, we started off with something that looks like a rectangle like this, where you had the length was d lambda and the width is d sigma, but it really is something more of this sort, right? So here we have, so this thing is really d sigma partial x over partial sigma, and this line over here is really d lambda partial x over partial lambda, right? And then you can connect these like this, and this really forms a parallelogram. Now, the length of the sides of the parallelogram, they should be fixed by the lengths of this d sigma and d lambda, which we really started with when we considered the rectangular case. Now, we want to understand what are they really. So if I look at this figure, this rectangle that we talked about just yet, you can consider this point and say that this point is really some coordinate. Let's just say it's sigma lambda. Now this would be mapped using this function as x of sigma and lambda. Now this parallelogram was created using this thing, that now suppose that if I consider this point, now this point is really, if you think about it, it's just sigma plus some d sigma, and lambda, you can see that it has not changed, so we have not moved in this vertical direction at all, so lambda remains lambda according to this thing. And so this gets mapped to what? Well, it gets mapped to x of sigma plus d sigma and lambda. And so that's how we could have drawn these vectors, right? Using this knowledge, we can draw these two vectors. You can do the same thing for lambda as well. So that's how we can draw this vector along the sigma side of the parallelogram from this thing, which is x of sigma lambda to x of sigma plus d sigma and lambda, which really means that this is just x of sigma plus d sigma and comma lambda minus x of sigma and lambda. Now you have this thing, right? This is a vector, and if I divide this vector by d sigma simply, then this is just really a derivative of x, right? So you can write it, I'll just say that it's just a derivative of x sigma and lambda. Now this derivative is really a directional derivative, and so it is in the direction of sigma, right? So I can write this whole thing as being equal to partial x vector over partial sigma. And so that's the reason why you see that we have these two vectors, and we have this vector which is pointing along this side of the parallelogram, and it's given by this thing, while this vector which is pointing along this side of the parallelogram is given by this thing. And now this more or less we are done with the problem. We just have to work with the geometry. And now consider, if I go down over here, consider that you have some two vectors a and b which make up the parallelogram. So we know that to write down the area of the parallelogram, you consider the length of one side, we'll call that a, and times the height of the parallelogram. But that height of the parallelogram is not just b, but it's really the sine component of this vector. So it would be b sine of theta, where this theta is simply the angle between these two vectors a and b. So that means that the area of a parallelogram, I'll just say, okay, let me write area of parallelogram. Ignore the spelling. It is just a b sine theta. So that's where you get the area of the parallelogram from. Now this thing is also, if you can remember, it also looks like the cross product of a vector and b vector, right? So you can then write down this thing in this form, that the area squared of this thing is just a squared b squared 1 minus cos squared of theta. We are just replacing sine squared as 1 minus cos squared theta. And this thing is really then just a squared b squared minus a squared b squared cos squared theta. But remember that this thing is really the dot product between a and b, because remember a dot b is given as ab cos theta. So I can write this thing down as a squared b squared minus a vector dot b vector squared. So that's really the area squared. Hence the area of this parallelogram is given as the square root of this whole thing, which is a squared b squared. You can write this as this, where these are just the magnitude of the vectors, minus a dot b vectors squared. So that is then the area of the parallelogram. Now we'll use this exact thing to write down the area of this world sheet, really, right? And we have these vectors as these things. Now all we have to do really is use these in this expression for area, right? So in this case, in our surface case, we can write this thing as the case of the surface where the vector A will just replace that by one of the directions. So that would, let's take this one to be sigma 1. So we'll have partial x over partial sigma, and we can say that vector B is the other direction or the other vector in that parallelogram, which was d lambda partial x over partial lambda. And now it's a matter of putting these things into this expression. And so the area, we'll call that dA, is simply given as the square root of d sigma partial x over partial sigma mod squared times d lambda partial x over partial lambda mod squared minus d sigma partial x over partial sigma dot d lambda partial x over partial lambda. And we have vectors on this x. And this is also squared. Now, I know this looks very lengthy, or you can even say that it looks a bit messy. But what we can do with this entire thing is we can simplify this thing as well. Now, if you look at this thing, you can see that every term in this expression has a factor of d sigma d lambda, d sigma d lambda, right? Both of these terms. And so what you can do is you can take that thing outside of the square root. So let's simplify this a bit on the next page. What I can do is I can write it more like dA is equal to d sigma d lambda times the square root of partial x over partial sigma, let's use this mod squared, times partial x over partial lambda mod squared minus partial x over partial sigma times partial x over partial lambda squared, right? So this is the dot product between these two vectors. Now, what I'm going to do from this point is just to make this a bit more in a simplified version, I can define a matrix. Let's call that matrix H. And we can define it in this way, that this term of the matrix is mod partial x over partial sigma mod squared. And this element can be partial x over partial sigma dot partial x over partial lambda, while this element can be partial x over partial sigma dot partial x over partial sigma, sorry, lambda. And this one, the final element, we can define it as the mod squared of partial x over partial lambda. And so this, if I define a matrix that looks something like this, then whatever is inside this square root, it is just the determinant of this matrix. So we have been clever about this, right? We have just used, we have just defined the matrix by looking at this expression inside the square root. Now what I can do is I can simplify this dA as dA being equal to d sigma d lambda and square root of the determinant of this matrix H. And it was that simple. Now we can write down areas, volumes, and hypervolumes in this form. Now, this thing h that we defined is really the metric of the surface, or the metric on the surface. And it is exactly like the metrics that you have as eta mu nu and g mu nu, where eta mu nu really appears in special relativity, while g mu nu is a metric that appears in general relativity. Now we know about metrics that they give you the information about or how do you measure distances really in a space. And so if they tell you on how do I measure distances, then they're by nature telling you how can you measure areas as well. And so to get the total area of this of your surface, all you have to do is integrate over all these areas. So I can just write this as integral of d sigma d lambda square root of determinant of this metric h. Now this was more or less the math that we needed, and now let's talk about the physics of what's happening over here, right? Okay, so what is really happening is again that you have a loop of string and it traces out a path, and this path is being traced out in space time really. So you can also say that the world sheet of this little loop of string that we have, it gets traced out as it evolves in space time. Now note that we only have to make a very few modifications to this entire thing that we have been doing so far to write down the area of a world sheet in both space and time dimensions. So first of all, we have been using this thing which is x vector. Now this was a three-dimensional thing. It was a, so what that means is that it was three component vector, and it gave you the coordinates of a three-dimensional space. Now we need, as we know in special or general relativity, we can write down something which is x mu, and this x mu is really a four component vector, and it gives you the coordinates of really space time, which is four-dimensional thing. Now just to keep things simple, we'll relate our things with the metric tensor of the flat space-time, right? So this is the metric tensor of the flat space-time. We'll not get into GR just yet. We'll keep things simple, and so we'll talk about the Minkowski metric. And so what we need to do is we need to basically replace our familiar Pythagorean notion of distances in regular space with this metric, the flat space-time metric, also called the Minkowski metric as well. We could have, of course, used the curved space-time metric g mu nu, but we want to keep things a bit more simple for this video, and so we'll just relate it to this eta mu nu. So with this now, eta mu nu, I can write down a new matrix for h, and that matrix would look, this is because how we computed the magnitude and dot products of vectors would be redefined with this eta mu nu, and so we'll not get into the gory details of that now, but we can write this h metric in terms of this flat space-time metric as eta mu nu partial x mu over partial sigma times partial x nu over partial sigma, and then this element is eta mu nu partial x mu over partial sigma partial x nu over partial lambda, and this would be eta mu nu partial x mu over partial sigma and partial x nu over partial lambda, and the final element is eta mu nu partial x mu over partial lambda times partial x nu over partial lambda. And so that's the new matrix for H, which means the metric is redefined in this thing. Remember that this H was or is a metric on this two-dimensional surface of the world sheet that we have been talking about. Now remember how we would write down the length of the particle's world line. If you remember, for a particle, the length is written as the integral of square root minus ds squared, right? And we would just flip the sign of this ds squared before we would take the square root, obviously, as it is negative. And now the same thing applies to the determinant of H in metric in the Minkowski space-time. And so then we can write down the area for our this you can say the world sheet or the string like thing. So the area can be written as the integral of d sigma d lambda square root of negative determinant of H. Now this is really the generalization of what you know about the length of the world line. So for the point particle case, really, remember we have we had this curve which is x mu of lambda. Now we're in the four dimensions, space and time, and we would not have this curve, right? So in this case, then the H matrix is really reduced to just one entry, which would be eta. It would be eta mu nu partial x mu over partial x mu over partial lambda times partial x nu over partial lambda as well. Now this thing, well, it's, you can call it the determinant, right, of a 1 cross 1 matrix, and it will keep the determinant of this thing is just going to it's just going to give you this thing, right? It's going to give you the number that you have over here. And so then you can find the length or the length of the world line. As you know, it is defined as the integral over this parameter lambda. Remember that this lambda parameter really was for this dimension where you just have one length, right? And so that is characterized by lambda, and hence you would have d lambda square root of negative of this thing, which is eta mu nu partial x mu over partial lambda partial x nu over partial lambda, right? Now the action for a point particle is then, you know, it is given as this length thing that you have over here. If I multiply this with minus m times c, then I can just write down the action, which is s, which is equal to minus mc times the integral of this whole thing over here, partial x mu over partial lambda partial x nu over partial lambda. So that's the action in terms of a point particle. Now what you can do is you can write down, do the same exact analogy for a string. And for a string, remember that you can write down the action really for the string as minus t over c, Now we're writing it in this form because T is really the tension in the string. And then you can have the same thing, the integral d sigma d lambda, which is, we are now writing the area, because in string we do not have length, but we would really have, for a world sheet it would be an area, and so that we just derived is given as this thing minus determinant of h. So this action, this is really for an action for something that is called a relativistic string, because we have been working writing this thing in a space-time thing, right? So the principle of least action in this case says that the string will evolve along this world sheet with an area which is really similar how a particle evolves using this world line with a length. So this action really here is the beginning of the string theory, and this action is also given a name. It's called the Nambu-Goto Action, and this is the point where you would be starting off your string theory course in more detail. So you can really say that this was just the tip of the iceberg of string theory.